Marhaba. Okay, in this session we want to take examples on mathematical induction technique. Okay, so we want to prove statements of the form for all n p of n for different properties p. For example, let's start with this theorem. We want to prove that for every for every positive integer n has this property. What is this property? That if you sum, look, what is 2k minus 1? It is an odd number. This summation, if you sum all the first n odd numbers, then you will get n squared. Okay, so to understand what is this, so this is the property p of n. Okay, this is p of n, and what we want to prove is that for all n, p of n is true. And we want to prove this is true where n is a positive integer, meaning that n is 1 or 2 or 3 or 4 and so on. So n takes values from here. Okay, so let's first understand what is the property p of n. For example, let's see what is p4. What does p4 mean? Okay, p4 means, it means that 4 has the property p. But what is the property? That if you sum the first 4 odd numbers, you will see why. So if you sum 2k minus 1, where k starts from 1 and stops at 4, what is this summation? So again, you start with k1, so this means 2 times 1 is 2 minus 1 is 1, plus, then you increment k to be 2, so this will be 2 times 2 minus 1, which is 3, and then you increment k to be 3, and this means 2 times 3, 6 minus 1 is 5, and then you take the last value of k, which is 4. 4 times 2 is 8, minus 1 is 7. And look, these are the first positive odd integer, first 4, okay, the first 4. So first 4 positive odd integers. Now the property says if you sum these, so what is the sum here is 16, and if you sum this you will get n squared. N here is 4, so this is equal to 4 squared. So this shows that 4 has the property p, but what we want to show is that any positive integer has the property p. So for example, if you want to see property for number 5, it means we add the first 5 positive odd integers, which are what? 1 plus 3 plus 5 plus 7 plus 9, and here you will get 25, and 25 is 5 squared. And this holds, which means what we want to show is that 1 plus 3, okay, sorry. Okay, what we want to show is that if you sum the first n positive odd numbers, so starting with 1 and then 3 and then 5 and then 7 and stopping at the nth one, and the nth one is 2n minus 1, you will always get n squared. Okay, so this is what we want to show. So we will show this by mathematical induction, and let's start proving this. Okay, so proof. So you say we will use mathematical induction, which means that base case. So first let p of n be this property, that so p of n is the predicate which says that the summation of 2k minus 1, where k ranges from 1 up to n, is equal to n squared. So this is a property about n. Okay, we want to prove that this holds for every n. So by mathematical induction, we need to do two things. First, we want to show that it holds for the first element in the domain, which is 1 here, because we are talking about positive integers. Okay, so we want to show that P of 1 is true. But what is P of 1? This says sum all numbers of the form k minus 1, where k starts from 1 and stops at 1. So what is this number? This is just 2 times 1 minus 1, which is 1, and this is equal to n squared, where n is 1 here. So this is equal to 1 squared. So this shows that the base case is true. So the property holds for the first positive integer. And now we want to say, if it holds for n, we want to show it holds for the next one. Remember the ladder picture. So now we will show the induction step. The induction step. So let n be any positive integer. Choose any one. Okay, so it's one or more. Suppose P of n is true, so that n has the property P. What is the property? It is this property, that the sum of 2k minus 1 from 1 to n is n squared. Now we need to show, we will show that P of n plus 1 is true. That the next positive integer has property P, that is, we need to show that the summation of 2k minus 1, where k starts from 0 and stops at n plus 1, this must be equal to the square of n plus 1. Okay, so we want to show this. Again, so this is our goal, to show this using the induction hypothesis, P of n. So let's start with the left-hand side. So now we start with the summation of 2k minus 1, when k starts from 0 and stops at n plus 1. But what is this? This is 1. When k is 0, we get 1 here. When k is 1, sorry, we should start from 1, right? We start, when k is 1, this is 1. When k is 2, this is 3, and then 5. And then when k is n, we get 2n minus 1, and then when k, we stop when k is n plus 1, sorry, right? Plus, and finally the last step is when k is n plus 1, so 2 times n plus 1 minus 1. So what is the sum of all of this? We know by the induction hypothesis that the sum of all of these is equal, okay, maybe I should write it in terms of summation of sigma notation. This is the sum of 2k minus 1, where k starts from 1 and stops at n. So the green line is equal to this summation plus what is left here. So 2 times n plus 1 minus 1. Now by the induction hypothesis, so let's write here IH, induction hypothesis, we know that this is equal to n squared, right? Because the summation of 2k minus 1 from 1 to n is equal to n squared. This is because we suppose that P of n is true. And what is P of n? Is that the summation from 1 to n of these numbers is n squared. Okay, so this is n squared plus 2 times n plus 1 minus 1, and this is equal to n squared plus 2n plus 2 minus 1 is plus 1, and you can check that this is indeed n plus 1 all squared. And this is what we wanted to show. We showed that the sum of 2k minus 1 from 1 to n plus 1 is n plus 1 squared. Right? This is what we want to show. We showed this assuming P of n is 2. This means by mathematical induction, so therefore we proved by mathematical induction for all n in the positive integers, we have that the summation of the first n odd numbers, so 2k minus 1, where k starts from 1 and stops at n, is indeed n squared. Okay, so this is what we proved, and this is the end of proof. Okay. let's take another example. The other example is that prove for all natural numbers now. So show that for all n in the natural numbers, the following is true, that the summation of 2 to the power k, where k starts from 0 and stops at n, is equal to 2 times to the power n plus 1 minus 1. Okay, so this is the property. So let me put it in a green frame. Okay, this is the property we want to show about a natural number n. What is it? That n has the following property, that if you sum the powers of 2 from 0 to n, you get the n plus 1 power of 2 minus 1. So for example, let's show that, say, p of 4 is true. What is the property p for 4? That if you sum the powers of 2 from 0 to 4, you have to get the fifth power of 2 minus 1. So what is this summation? This is 2 to the 0 plus 2 to the 1, 2 to the 2, and you stop at 2 to the 4. And this is 1 plus 2 plus 4 plus 16. And this is 23, right? Now, is this equal to 2 to the power 5 minus 1? No, because I'm missing something, right? This is 2 to the power 3 plus 2 to the power 4, and here we are missing an 8. Okay, so 2 to the power 3 is 8 plus 16, and this should be 28 plus 3 is 31, right? 1 plus 2 is 3 plus 4, 7, 7 plus 8 is 15, plus 16 is 31. Now, so this is 31. Is 31 equal? So 31 is equal to 2 to the power 5 minus 1, right? 32 minus 1 is 31. So this means that 4 has the property p. So this is what we want to show, that this property holds for every natural number. Okay. So let's show this. How do we show this? By mathematical induction. We need to show that the property holds for the first number, which is 0. Okay, so base case. Show that p of 0 is true. What is p of 0? That the summation of the powers of 2, where k starts from 0 and stops at 0, and this is just 2 to the 0, which is 1, we need to show that this is equal. So is it equal to 2 to the power, look, n is 0. 0 plus 1 is 1 minus 1. But yes, 2 minus 1 is 1, so it's equal. This shows that the base case is true. Now, so we stepped the first step of the ladder. Now we want to show that whenever we reach a step in the ladder, we can reach the next step. So this is the induction step. The induction step. Let n be any natural number. So choose any natural number whatsoever. And suppose it has property p. So suppose property p holds for n. We need to show that p of n plus 1 is true. Okay. In other words, we need to show that if we sum the powers of 2, where k starts from 0 and stops at n plus 1, you will get, look, 2 to the power n plus 1 plus 1. So we get n plus 2 minus 1. This is what we want to show. So we need to show this, which is in the black frame. Okay, let's start with the left hand side, use the induction hypothesis and get the right hand side. So now start with the left hand side, which is the summation of all powers of 2, where the powers range from 0 up to n plus 1. And this is 2 to the power 0 plus 2 to the power 1 plus up to 2 to the power n, and we stop at 2 to the power n plus 1, right? K stops when this is the upper limit of the summation. But now again, we can write, we care about these numbers because they are involved in P of n. So we know that these are the summation of the powers of 2 from 0 up to n plus the last term. Okay, by the induction hypothesis we know that this sum is equal to 2 to the n plus 1 minus 1 plus 2 to the n plus 1, right? Now what is this? This is this number, say call it x, and this number is the same, x, so x plus x is 2x, so this is 2 times x minus 1, and so here we can add the exponents since we have the same power and basis, so this is 2 to the power n plus 1 plus 1, so this is n plus 2 minus 1, and this is what we wanted to show. So this shows that P of n plus 1 is true. Okay, where did we use the induction hypothesis? At this step. We know that this summation is equal to this number by induction hypothesis because we assume that n has the property P, and what is the property? That the blue number is equal to the green number. These are okay. So by induction we finish our proof by saying by induction or mathematical induction we proved that for all n in the natural numbers the following is true, which is the summation of all the powers from k equals to 0 up to n is 2 to the n plus 1 minus 1. Okay, so you choose any natural number, sum the powers of 2 from 0 to this number n, you will find out that the summation is equal to 2 times the n plus 1 power minus 1. Let's have one final example for this session. Okay. We want to show that, for all integers, for all n bigger than or equal to 4, the following is true, that if you raise 2 to the power n, you will get a number strictly less than n factorial. Okay, so this is P of n. This is a property about n, which says that if you raise 2 to the power n, you will get a number strictly less than n factorial, starting from 4. So notice that P of 3 is false, because what's P of 3? It says that 2 to the 3 is less than 3 factorial, but this is wrong because this is 8. 2 to the power 3 is 8, and 3 factorial is 3 times 2 times 1, which is 6. Okay, so 8 is not, so this is false. 8 is not less than 6. Okay. Now let's prove this by induction. So again, we want to show this is by induction. So base case. The base case is to show that the property holds for the first number. And what is the first number here? Is n is equal to 4. So show that P of 4 is true. And what is the property P for 4? It says that 2 to the power 4 is 16. And we know that 16 is strictly less than 24, and 24 is 4 factorial. right? 4 times 3 times 2 is 24. So this shows that 2 to the power 4 is strictly less than 4 factorial. And this is the property P for the number 4. Now let's do so this is the base case. Let's show the induction step. We need to show that for every n bigger than or equal to 4, if P of n is true, then P of the next one of the successor is also true. So how do we prove such a statement? We choose an arbitrary, so let n be an arbitrary integer with n bigger than or equal to 4. So choose any integer bigger than or equal to 4. And suppose P of n is true. So suppose P of n is true. This is the induction hypothesis. Okay, what does it mean? That it means that for this n we chose, 2 to the n is strictly less than n factorial. And now show that, right? This is how we prove in a direct way conditional statements. We assume the hypothesis, we show the conclusion. So show that P of n plus 1 is true. And what does this mean? i.e. 2 to the power n plus 1 is strictly less than n plus 1 factorial. This is what we need to show. So let's start with the left hand side. So now the left hand side is 2 to the power n plus 1. And all the information we have is P of n. We assumed P of n is true. So we need to use this piece of information. What's P of n? Is that 2 to the n is strictly less than n factorial. So we need to create 2 to the n from here. How can you obtain 2 to the n from 2 to the n plus 1? Okay, I'll tell you the trick. That 2 to the n plus 1 is equal to 2 times 2 to the n. Right? If you sum the exponents, you get 2 to the n plus 1. This has exponent 1. But now, by the induction hypothesis, we know that 2 to the n, so 2 is 2, but we know that 2 to the n is strictly less than n factorial. So this 2 to the n is strictly less than n factorial. Now, look, what do we want? We want n plus 1 factorial. We have n factorial, so all what will remain is to find some n plus 1 here, because I don't know if you remember that n plus 1 factorial is equal to n plus 1 times n minus 1, so times n factorial. Okay, so we know this. That n plus 1 factorial is n plus 1 times n factorial. So we already have n factorial. It remains to create some n plus 1. But we have here 2. Okay, look at this. Let me write it here. What do we know about n? We know that n is bigger than or equal to 4, right? From here. Let n be an integer which is bigger than or equal to 4. And we know that n is strictly less than n plus 1. And we know 4 is strictly bigger than 2. So this means that 2 is strictly less than n plus 1. So we can replace this 2. So this number is strictly less than n plus 1. Why? Because n plus 1 is strictly bigger than 2, okay, times n factorial. And this means, what is n plus 1 times n factorial? This is n plus 1 factorial. So this work is on the side. So since n is bigger than or equal to 4, we know that n plus 1 is bigger than 2. So we can replace 2 by n plus 1, preserving the inequality, the strict inequality. And so this is what we want. We prove that 2 to the n plus 1 is strictly less than n plus 1 factorial. right? This is showing that n plus 1 has the property p. Therefore, by induction hypothesis, we proved that for all n bigger than or equal to 4, 2 to the n is strictly less than n factorial. So this is in terms of the complexity of algorithms, says that algorithms which need 2 to exponential steps to finish are faster than those algorithms which need factorial steps to finish.